Welcome. In this lecture, we're going to go through how we would approximate a two-variable function using a tangent plane, just in kind of analogy with how we approximated a one-variable function using a tangent line. Okay, so let's get started. So here's our picture. So we have our x-axis like this. It's going to go back like that. And our y-axis. And we have our z-axis, maybe would give us, a third axis. And then we're going to say we have the graph of a function is going to be up here. So we have some kind of graph. We have a function and we have its graph up here. So this is z equals f of, and this would be, f of x and y. Actually, I want to label it over there. So this is going to be z equals f. This is the graph of this. So what does that kind of mean? I don't know why I'm putting all my caps back on. It's not necessary. So what I mean here is that, right, so if I take a point, so we're going to take some kind of point, AB. So I'm going to take some point, and we're going to look at it in the XY plane here. So maybe this point is at here. So this is some kind of point AB. I plan things out carefully in my notes to make sure everything's where I want it, and then I get excited drawing, and I draw things exactly where I purposely didn't put them. So, but that's that's life when you get excited easily as I do. Okay, so then we have, so maybe this is some kind of point AB. And then if I go up, so this is where actually, again, we call this AB, but it's really AB0. And if I go up until I hit the graph, right, I get some kind of point here. And this point here is going to be AB, f of AB, right? So this is going to be B, f of AB. So this is going to be A, B, f of AB, right? And then at this particular point, I have this tangent plane. Right? So this is this plane. And what is this plane's equation? So the equation of this plane is going to be, so this is the tangent plane. And it's going to be 2f, so our function f, so 2f at this kind of, this point, right, this point A and then B, right? And what is its equation? So its equation is going to be z equals, and then I have, it starts with f of AB, so that same point, AB. And that basically moves me up to that particular location. And then I go over some amount in the partial, based on the partial of x, but I plug into the partial derivative of x, this point AB. And then I multiply that by x minus a, so x minus, and I'm making sure to always put this, these a and b, so that you can see, right, because this is the tangent plane 2f at AB. So this stuff all depends on your function and your point. So, and then we take the partial in the y direction, and this is again AB, and now instead we're taking the x minus, sorry, now this is the y minus b. Okay, so this is the tangent plane. This is the equation for the tangent plane. And then what does that do for me? That tells me if I take a point that's very close by, right? So let's take a point. Now we're taking a point in here that's close by. Okay, so this point is going to look like so this point is going to be xy f of xy. So this looks like xy f of xy. Like this. So this is a point here. And what's going to happen is that, you know, these 2 points are on here, but then I can approximate. Right, so this is my graph here. But I can approximate this by going up to the tangent plane, right, and getting a point here, which is going to look like right, what does this point look like? This point's on the tangent plane, so I have x, y, and then I have this whole big, huge thing. So I have, oh, my AB got kind of, the order there somehow got swapped in terms of color. I've been doing my, I don't know if you noticed this, that I swapped these in this particular one. I swapped the colors for some reason. Only in this particular one. So this was A and that was B. Okay, and so now instead of this going into the function, this actually goes into our whole tangent line equation. So this goes into, so this is, we're going to call this the linearization, right? This is the linearization at, the linearization at AB. Right? But then we're evaluating it at the point xy. Okay? So then this third coordinate here is going to be L of, well, that linearization. So I can put down there, this is like AB, but this is going to be evaluated at xy. So I'm just sticking this x and y into that equation over there, but it's like kind of long, so I don't want to rewrite it all here, but it's this equation here. Okay, so just like with the tangent line, this approximates, these points should be pretty close. As long as the x and y are pretty close, then those outputs should be pretty close. So this gives a pretty good approximation for the graph, for the values of the function. So what are some kind of consequential approximations? So here are some consequential approximations. Okay, so the first one is that if I take f of xy, this is going to be approximately equal to what I would get, like I was just saying before, if I actually kind of put this into, so this is f of AB plus fx evaluated at AB, so the partial with respect to x evaluated at AB, and I'm actually going to take my x minus a. Right, and then I want to add to that, so I have the partial with respect to y evaluated at AB, and then this is y minus b. Okay, and so this actually gives me an approximation for my output of my function evaluated at anything that's kind of close to AB. The other thing that happens is if I want to look at my output error, so this is like my output error. That this is approximately equal to, so I have the partial x AB, and then I have this x input error. So this is my x input error. And then I'm going to add to that, right, if I add to that my partial with respect to y, AB, and my y input error, then that would actually give my output error, like my error in F. Okay, so what's going on here? We have, just like in the circumstance of having the, just like in the circumstance of the tangent line approximating, like it's close to the graph of the function at that point, which means that the equation for it gives an approximation for the value of that function at that point. We have a similar thing here, but now this is like a two-dimensional picture where I have a plane that's like, you know, on a graph, on a two-dimensional graph, and the y, you know, the value that I would get out at the tangent plane there, like its height, would actually give me a good approximation for the function as long as my x and y are close to my a and b. Notice that the tangent plane depends on my a and b, just kind of like our tangent line depended on your input point. But it also gives you, so if I wanted to approximate my output error, then it's going to be approximately equal to what I get when I take the partial derivative with respect to x, and then my input error, and then add that to the partial derivative with respect to y, evaluated AB, with my output error. Okay, so this is just an approximation technique with a really nice picture that goes with it. This is, again, a linear approximation. There are higher order approximations. Okay, so I hope that made some sense, and I will see you in the next lecture.